Hello and welcome to the next lecture in machine learning for core engineering disciplines. In the last lecture, we derived the equation for the best fit parameters in a linear regression fit, and we used concepts from linear algebra to be able to do that. So, we will take off from there, and in today's lecture we will try to assign confidence intervals to the best fit parameters, because we need to know how reliable the estimates that we obtained for the intercept or for the slopes or weights of various features are. So, that is what we will be doing today. So, the title of the topic is confidence intervals for linear regression parameters. Right. So, now we have to start our discussion with what exactly is a confidence interval. So, let us define what a confidence interval is. So, a confidence interval Ci at the C equals 100 times 1 minus alpha percent refers to an interval around a stochastic quantity in which it will lie C percent of times, right, and a related quantity is the significance level which is denoted as alpha. Right. So, we are trying to find an interval, right, in which the stochastic quantity will lie. So, we are trying to find the interval, right, in which your linear regression parameters will lie, and every time you compute the linear regression parameters, right, if your sample changes, the value that you will get for that parameter will change, right, and we are trying to find, right, is there a particular interval in which confidently we can say that it will lie, and that is what this concept is all about. So, if you look at the relationship between the confidence level C and the significance level alpha, it is as follows. So, if alpha has the value 0.01, then the confidence level we are aiming for is 99%. If the alpha value is 0.05, the confidence level we are aiming for is 95%, and if the alpha value is 0.1, then we are aiming for a confidence level of 90%, right. So, this is what we want to do for the linear regression parameters. Now, a related concept is that of hypothesis testing, which a lot of people working especially in the biological sciences are very familiar with, and this hypothesis testing refers to the validation of a certain statement called the null hypothesis, which is denoted as H naught, as opposed to a contrary statement called the alternate hypothesis. Which is denoted as HA, right. And all this hypothesis testing is also done with respect to this confidence level. To a given significance level. Okay. So, now assigning these confidence intervals or carrying out hypothesis testing that requires knowledge of the underlying probability density function of the variable of interest, right. So, the variable of interest right, and this can be different for different people. It could be the population mean or it could be the population standard deviation. For us it will mainly be the population mean, and particularly the population mean of the linear regression parameters, right. So, we want to see how confident can we be about the population mean of the linear regression parameters, which included beta naught, beta 1 and so on and so forth, right. So, the hypothesis tests on the population mean, there are mainly two such tests. So, if you look at hypothesis tests for the population mean, there are mainly two types of tests. One is called the Z test, right, which is based on the normalized normal distribution. So, this can be carried out if the population standard deviation, population sigma, is known, right. Under that scenario, the Z test is applicable for the population mean. The other test that can be used is called the student's T test, and this is applicable if the population standard deviation is unknown, right. And in our case, particularly when we are talking about linear regression best fit parameters, we will not really know what the population standard deviation is for the linear regression parameters. So, this particular case will be more applicable to us, and therefore, we will be using the T test to assign the confidence intervals to the best fit parameters of linear regression. Okay. So, let us go ahead and see how this is done. Nevertheless, I want to introduce the concept of the Z test to you, so that if you want to use it elsewhere, you would be able to do it. Okay. So, let us consider a Z test, and remember this is a test for the population mean, right, lying in a certain range. So, to do this test, let us consider an independent sample right, y1, y2 up to yn collected from a population with a known population standard deviation. So now what you do is you want to look at the sample mean, right, because that is the estimator we have for the population mean, and you know that the sample mean is simply the arithmetic average of all the samples, right, the values that were collected. And similarly the sample variance, right, can also be defined, and we discussed this in one of the previous lectures. It is 1 over n minus 1 sum I going from 1 to n yi minus y bar whole square, right. Now if you look at how the sample mean is distributed, right, that is what will be required to carry out this hypothesis testing or to assign confidence intervals. So to know how it is distributed, we have to compute its expectation as well as its standard deviation of variance. So let us look at the expectation of the sample mean, and this is something we have encountered before when we studied that expectation is basically a linear operator. So what that would imply is this 1 over n and the summation, right, are going to come outside the expectation operator, and then we are going to use the fact that each of these yi's is sampled from the same distribution, right. So the expectation of each yi is equal to the true population mean, right. So therefore the value of each term inside the summation is mu, and we are adding it up n times. So we will get n mu by which the n's will cancel, and simply we will get mu as the expectation of the sample mean, right. Now in a similar manner we can compute the variance of the sample mean, right. So the variance of the sample mean will simply be the variance of 1 over n sum I going from 1 to n yi, and in the case of the variance the constants come out but they are squared. So it is 1 over n squared and then sum I going from 1 to n variance of yi, and this becomes 1 over n squared times n sigma squared. So that is sigma squared divided by n, right. So that is the variance of the population mean. Now at this point we need to assume something about how the yi's are distributed, right, because otherwise we will not be able to compute more than just the mean and the variance. So if we assume each yi to be normally distributed, then, right, the sample mean will also follow a normal distribution, right. So yi will be a normal distribution with mean mu and variance sigma squared. Now in this case your y bar will also follow a normal distribution with mean mu and standard deviation sigma squared divided by n, right. So now at this point for the z test we define a random variable z that is given as y bar minus mu divided by sigma divided by root n, right. So we have normalized this sample mean, right, we have zeroed out its mean and then also divided it by its standard deviation, right. So now what will happen is the z statistic will follow a normal distribution, but its mean will be 0, that is because we have subtracted out the mean from y bar, and its standard deviation will be 1 because we have normalized the variable, right. So z will follow a normal distribution with mean 0 and variance 1 or standard deviation equal to 1, right. And with this z statistic we can now do hypothesis testing or we can assign confidence intervals, right. And when we look at hypothesis testing, there are two alternatives. One is called a one-sided test, and alternatively you can also do a two-sided test. Okay. So, I will tell you how these two tests are done. So, for the two-sided test, if you plot the probability density function of the random variable z, then you know that it is a bell curve with mean 0 and standard deviation sigma divided by root n, right. And now you know that you have the significance level alpha. So, if you have a two-sided test, right, then this region and this region, right, they are both partitioned to alpha by 2, right, to give a total probability of alpha. So, what remains in between becomes 1 minus alpha, right. So, what remains in between is 1 minus alpha, and in this case the null hypothesis H naught is rejected if z is greater than z 1 minus alpha, right, the z that you compute, right, based on your test statistic. If that is greater than z of 1 minus alpha by 2, or z is less than z alpha by 2. So, either it lies in this region or this region, right, then the null hypothesis is rejected, and otherwise the null hypothesis right cannot be rejected. Okay, so that is for a two-sided test, and instead you could also do a one-sided test. So, let us look at how that is done. So, as the name suggests, here we are just looking at one side of the distribution, right. So, if you have f of z as a function of z, and again you have the bell curve, right, and here this region has probability alpha. So, this becomes z of 1 minus alpha, right, and the remaining, right, has probability 1 minus alpha. Now, in this case the null hypothesis H naught is rejected if z is greater than z 1 minus alpha, and otherwise the null hypothesis has to be retained, cannot be rejected. So, this is how the z test works, right, and I encourage you to go into other books and see examples where the z test is applied or even the t test is applied, because this is primarily a course on machine learning. So, I just want to introduce the concept of confidence intervals, and hypothesis testing is a related concept. So, we will not be getting time to delve into all of this very deeply. So, with that done, let us shift our attention to the student's t test. So, this, to remind you, is a test for the population mean when the population standard deviation is unknown. which is what will happen in most realistic cases, including our linear regression problem. Right. So, let us see how this works. So, in this case you have to define the random variable t instead of the random variable z. So, the random variable of our interest now is t, which is defined as y bar minus mu divided by s divided by root n. So, instead of having the population standard deviation, here you have the sample standard deviation, and that is because the population standard deviation is unknown. Now, this particular random variable, it can be shown that it follows the student's t distribution with n minus 1 degrees of freedom. So, it follows the student's t distribution with n minus 1 degrees of freedom. Okay. So, now if we want to assign confidence intervals, we will be able to say that the probability of your random variable t lying between t alpha by 2 and t 1 minus alpha by 2 will be equal to 1 minus alpha, right. And clearly we are following the two sided approach, because we want a confidence intervals plus and minus the linear regression parameter. You could also do a one sided test, but that would only give you an upper bound or a lower bound. If you want bounds on both sides, you will have to write it in this particular way, right. So, now you know what the t random variable is. So, t alpha by 2 less than y bar minus mu by s divided by root n will be less than t of 1 minus alpha by 2, right. And you can also put equals signs here, and this is what is the probability of this t random variable lying in this range, right. Now, what you can now do is, since s is a positive number, square root of n is a positive number, you can multiply s divided by root n on both sides. So, that becomes a probability of t alpha by 2 times s divided by root n less than equal to y bar minus mu less than equal to t 1 minus alpha by 2 times s divided by root n, and this probability becomes 1 minus alpha. And finally, we are trying to find the confidence interval for mu. So, we have to write this in terms of mu, and that would involve subtracting it out, right. So, multiplying it by a minus sign. So, the inequality would now get flipped. So, you will have a probability of minus t 1 minus alpha by 2 times s divided by root n will be less than equal to mu minus y bar, and that will be less than equal to minus t alpha by 2 times s by root n, and this probability will be equal to 1 minus alpha. And finally, we have derived the confidence interval. If you add y bar to all terms in this inequality, you will have y bar minus t 1 minus alpha by 2 times s divided by root n will be less than equal to mu, and that itself will be less than equal to y bar minus t alpha by 2 times s divided by root n. Okay. And thus we have managed to derive the confidence interval for the population mean. So, this is the lower bound for the population mean in the confidence interval, and this is the upper bound for the population mean in terms of the sample mean, right. So, this recipe can now be extended to find the confidence intervals for the linear regression parameters. So, let us see how that is done. So, now that we know how to find the confidence intervals for the population mean, we have to repeat this exercise for linear regression parameters. So, we want to find the confidence intervals for linear regression parameters, and if you remember your beta hat, the optimal set of parameters, that was equal to x transpose x inverse x transpose y, where y was the true values, right, of the target variable and x was the matrix of features, right. Now, this is the quantity on which we want to assign the confidence intervals. So, we need to know the sample mean, right, and the sample standard deviation to be able to do that, right. So, we need to know the sample mean and the sample standard deviation to be able to assign the confidence interval for the population mean, right. So, to assign the confidence interval Ci to beta hat, we need to know the mean, right, expected value of beta hat, and we need to know the variance of beta hat. So, let us see how this is done. So, to do this, we will assume that the errors epsilon in prediction are normally distributed. And this is typically true, right. We know that errors are usually normally distributed. So, to find the expected value of beta hat, we will take the expectation of x transpose x inverse x transpose y, and your y, right, the true value is basically x times beta plus some error epsilon, right. So, these are the actual parameters and this is the error, right, in the model. So, using this notation, we will be able to find the expected value of beta hat, right. So, your expected value of beta hat, that is equal to the expected value of x transpose x inverse x transpose y, and this y we know is equal to x beta plus epsilon. Okay. And now we will be able to greatly simplify this, as you shall see, right. So, this first term becomes x transpose x inverse x transpose x beta, and then you have a second term which is x transpose x inverse x transpose epsilon, right. And this is simply the identity matrix. So, you can simplify this to I beta, right, the identity matrix, plus your x transpose x inverse x transpose the expected value of epsilon, right, because this is the data matrix that comes out, because these are all constants, they do not change. Now, this becomes expected value of beta, and the expected value of the error is basically 0, because the errors are both positive and negative. So, on an average the expectation value of the error is 0, it is normally distributed. So, what we have proved is that the expected value of beta hat is simply equal to the expected value of beta, and this is equal to beta. So, this means that beta hat is an unbiased estimator for beta, right. So, that is actually very nice to know, right, is an unbiased estimator for the actual parameters, right, beta, which is what we had used to denote it here. So, now we are almost there. So, we need to now find the variance of beta. So, that is also something that is needed, and to do this, to determine this, we will use the covariance matrix. Okay. So, how do we do that? The covariance matrix, as you know already by now, is simply the expected value of beta hat minus beta, that is the expected value, times beta hat minus beta transpose, right. This is something we had already seen, and using the knowledge that y is equal to x beta plus epsilon, which we had introduced on the previous page, and beta hat equals x transpose x inverse x transpose y. Combining these two, we find that x transpose x beta hat equals x transpose y, and from here you also know that x transpose y equals x transpose x beta plus x transpose epsilon, right. So, this allows us to compare the values that we obtained for x transpose y, so that x transpose x beta hat will be equal to x transpose x beta plus x transpose epsilon. And finally, if you simplify this expression, you will be able to find that beta hat minus beta, right, that is equal to x transpose x inverse x transpose epsilon. So, this is very nice because we can plug this back into the covariance expression. So, the covariance of beta hat, this becomes the expected value of beta hat minus beta times beta hat minus beta transpose. So, that becomes x transpose x inverse x transpose epsilon times x transpose x inverse x transpose epsilon whole transpose. Okay. So, this seems like a complicated expression, but we should be able to simplify this, right. So, upon simplification, right, what happens is you will be able to show, right, and I encourage you to try this on your own and look at some textbooks if you are unable to do that, but requires some kind of manipulation of these matrices. You should be able to show that it is equal to x transpose x inverse times the expected value of epsilon epsilon transpose, right. So, this is the covariance. Now, if we want to look at the variance, we just look at the diagonal, right, elements. So, the variance of beta hat will be the diagonal elements of this particular matrix x transpose x inverse, right, times the expected value of epsilon epsilon transpose, and this becomes equal to diagonal entries of x transpose x inverse times the variance of epsilon, right. So, this we have obtained a really nice expression for the variance of beta hat, right. So, this is very useful here, and you know the variance of epsilon, that is simply sigma squared. Okay. So, your variance of beta hat becomes sigma squared diagonal of x transpose x inverse. right. So, your beta hat then is also normally distributed with the mean beta, the true parameters, and the variance equal to sigma squared diagonal of x transpose x inverse, right. So, now we can use the student's t distribution, right, because we do not really know sigma squared. So, we will use the sample standard deviation instead, and this will force us to use the student's t distribution. So, essentially your beta hat minus beta divided by square root of s squared diagonal of x transpose x inverse, this will be distributed with the student's t distribution with n minus p degrees of freedom, where p is the number of parameters in the linear regression model. And finally, using the expression that we derived a little while ago, right, which you saw that this particular expression, we will be able to assign the confidence intervals for beta, right, which is the true value of your model parameters. So, using the expression derived above, you will be able to say that the confidence interval, right, for the true parameter value, that is equal to beta hat minus t n minus p comma 1 minus alpha by 2 times square root of s squared diagonal of x transpose x inverse, and the upper bound of this will be beta hat minus t n minus p comma alpha by 2 times square root of s squared diagonal of x transpose x inverse, okay, and that is at the 1 minus alpha level, right. So, if we use alpha is 0.01, we will obtain the 99% confidence interval. So, that is a very strict limit. However, we can change the value of alpha, and that will give us the relevant confidence interval, right. So, I hope from this slightly complicated derivation you are able to appreciate how we can assign confidence intervals to the linear regression parameters, and this s squared, right, which appears here, which is the sample variance in the error, that can also be estimated as follows. Again, here we have to normalize by 1 over n minus p, because that is the degrees of freedom, and you have to just calculate this particular quantity, and that will give you the standard deviation, the sample standard deviation or the sample variance of the error, right. So, with this we come to the end of our lecture today. We went through a very detailed derivation of how we can assign confidence intervals, right, to variables that are distributed with the standard with the student's t distribution, and this happens because we do not know the population standard deviation, and instead we have to approximate it with the sample standard deviation. And I hope you will now be able to assign confidence intervals to your linear regression parameters. So, in the next lecture what we will do is we will try to understand variants of linear regression, especially that are useful in ameliorating the important problem of overfitting. Thank you, and I will see you in the next class.